As we explore our classification models, it's important to step back and ask, how accurate are our results? In this two-part video, we'll explore multiple evaluation tools, starting with some key metrics: sensitivity, specificity, and overall accuracy. To begin, let's consider a logistic regression model of whether or not it rains tomorrow based on two predictors: today's 9 a.m. humidity and the number of hours of bright sunshine. We can then use this model for rain classification. For example, we might say that if the probability of rain, as calculated from this model, is at least 0.5, we'll predict rain. Or, translated to our predictor values, if humidity is at least 38.85 plus 12.04 times sunshine, we'll predict rain. Otherwise, we'll predict no rain. This classification rule is represented by the black line on this plot of the humidity and sunshine levels on our sample of rainy and non-rainy days. Clearly, it isn't perfect. Some of the rain outcomes, the orange dots, fall below the classification line, thus would be misclassified as no rain. Similarly, some of the non-rain outcomes, or the black dots, fall above the classification line, thus would be misclassified as rain. An in-sample confusion matrix provides some insight here. This matrix breaks down the number of true negatives, or the number of days on which we accurately predicted no rain, the number of false negatives, or the number of days on which we predicted it wouldn't rain, the number of true positives, or the number of days on which we accurately predicted rain, and the number of false positives, or the number of days on which we predicted it would rain, but it didn't. Examples of each of these outcomes are displayed in the plot. We can use this matrix to calculate some important metrics of classification accuracy. Let's start with the overall accuracy of our model's classifications, that is, the proportion of all observations that are correctly classified. In total here, there are 4,608 data points in our sample, and in total, 3,744 of these were correctly classified. This includes 3,119 true negatives and 625 true positives. Thus, overall, 81.3% of the rain, no rain classifications were correct. The sensitivity, or true positive rate, focuses on the ability of our classification rule to detect rain. It calculates the proportion of rainy days that are correctly classified as rain. In total, there are 1,188 rainy days in our dataset, plotted here. Of these, only 625 fall above the classification line, thus are true positives. In turn, our classification rule only correctly classifies 52.6% of rainy days as rain. In contrast, the specificity, or true negative rate, calculates the proportion of non-rainy days that are correctly classified as such. In total, there are 3,420 non-rainy days in our dataset, plotted here. Of these, 3,119, or nearly all of them, fall below the classification line, thus are true negatives. In turn, our classification rule correctly predicts no rain on 91.2% of non-rainy days. In summary, our classification rule using a 0.5 probability threshold has high specificity, meaning it's good at anticipating when it won't rain, but low sensitivity, meaning it's bad at anticipating when it will rain. To improve sensitivity, we can make it easier to predict rain by lowering the probability threshold. For example, suppose that if there's even a 5% chance of rain, then we'll predict rain. In this case, what combined levels of humidity and sunshine would lead to a prediction of rain? Let's translate this rule. First, when the probability of rain is at least 0.5, the log odds of rain is at least negative 2.94. Thus, our logistic regression equation is at least negative 2.94. Solving for humidity, we can move the constant and sunshine terms to the other side of the equation. And then combining the negative 2.94 and 1.01 constants produces one constant of negative 1.93. We can then divide both sides by the 0.026 humidity coefficient. Thus, if humidity is at least negative 74.23 plus 12.04 times sunshine, we'll predict rain. This rule produces the classification regions shown here. Let's compare the performance of this classification rule to our original rule, which used a probability threshold of 0.5. These two rules can produce different classifications, thus have different confusion matrices. Based on these confusion matrices, notice that dropping the probability threshold from 0.5 to 0.05 resulted in a jump in sensitivity from only 52.6% to 98.1%. That is, our new rule correctly predicts rain on 98.1% of rainy days, or almost all of the time. But this comes with a cost, a drastic drop in specificity from 91.2% to 18.2%. Essentially, by lowering the threshold to predict rain, we not only end up with more true positives, but more false positives. Thus, our new classification rule correctly predicts no rain on only 18.2% of non-rainy days. This outcome reflects some general patterns in classification algorithms. First, we get to pick which probability threshold to use in our classifications. Thus, we have some control over the classification properties of our algorithm. But we have to consider some trade-offs. We observed that if we decrease the probability threshold, sensitivity increases, but specificity decreases. Similarly, if we were to increase the probability threshold, making it harder to predict rain, specificity would increase at the cost of a decrease in sensitivity. In part 2 of this video, we'll explore some considerations in choosing a probability threshold. And for your future reference, the final slide here provides formulas for the 3 classification metrics explored in this video.